Hello friends, in this video I'm going to discuss about the flow of viscous fluid through two parallel fixed plates, which is again the part of viscous flow module in applied fluid mechanics. In last video I have discussed about the flow of viscous fluid through a circular pipe, which is nothing but the Hazen-Poiseuille law. I have discussed about the derivation of that equation. We have seen the shear stress distribution as well as velocity distribution, and we try to solve a small example based on that equation to understand the use of the equation. Now in this video I'm going to discuss about first of all the derivation of the equations, and that too for shear stress distribution, velocity distribution, as well as we'll see the ratio of maximum velocity to average velocity, and also we'll see the pressure drop in terms of average velocity. And lastly, we'll try to solve a small example to understand more about this concept and to know the exact use of these equations. Right. So let's begin. So as you can see here in this figure, consider viscous fluid is flowing between two parallel fixed plates, which is now located at distance capital B apart, and also consider a small rectangular fluid element of length dx and thickness dy, which is located at a distance small y from the lower fixed plate. Also consider a width of the element in the direction perpendicular to the paper as a dz, right? So I hope you understood. This dx is the length of the element, dy is the thickness of the element, and dz would be the width of this element, which is will be in the direction perpendicular to the plane of this paper. So if we consider this case, and this right side is the direction of the flow, the forces which is going to act on this fluid element are starting with the pressure forces due to the pressure intensities, right? So let's assume that the P is the pressure intensity on the face AB of the fluid element, and the similar way the pressure intensity on the face CD as P plus curly P by curly X into dx, right? So with this, the forces which is going to act on this fluid element are, the first one is the pressure force, that is P into dy dz, that will act on the face AB. The another pressure force will act on the face CD, and that will be P plus curly P by curly X into dx into dy dz, and that will be on the face CD. And similarly there will be shear stresses developed, so due to that shear force will going to act. The third one will be shear force, which is acting on the face AC, that is on the bottom side of this fluid element, which is given by tau into dx dz. And the shear force which is going to act on the face BD, that is the top side of the fluid element, which is given by tau plus curly tau by curly y into dy dx dz. So in this case we have four different forces that were going to act on the fluid element, right? If you remember, in the case of viscous fluid flow through a circular pipe, there were only three forces acting on it. The additional shear force here acting is on the top side of this fluid element, right? Because this is not the circular fluid element we have considered, but this is the rectangular fluid element, right? And this is the case for two parallel fixed plates. Kindly note that. Now if you understand here, these are the forces. So assuming that this is the case of steady and uniform flow, there won't be any acceleration, and hence you can say the resultant force in the direction of the flow would be zero. So that's why there is no acceleration. Taking the summation of these forces and equating it to zero, we can say P dy dz minus P plus curly P by curly X into dx dy dz. That would be in the opposite direction, so the sign convention is minus. Then tau dx dz, again the shear force acting on the bottom side of the fluid element, that is in the opposite direction, and the plus tau plus curly tau upon curly y dy dx dz, the another shear force that will act in the direction of the flow, that's why the sign is plus, is equals to 0. If you summarize this equation, if you try to simplify this equation, the form will be the common term will going to get cancelled. As you can see here, the common term would be, you can say, this p dy dz, and this p dy dz will going to get cancelled. Similarly, this tau dx dz and tau dx dz will get cancelled. So the remaining term will be minus curly p upon curly x dx dy dz plus curly tau upon curly y dx dy dz is equal to 0. Or you can say curly p upon curly x is equal to curly tau upon curly y. Let's say this is your equation number 1. Now, as I have just told you that we are going to discuss about the shear stress distribution as well as velocity distribution. So here what we'll do, before starting with shear stress distribution, we'll try to see velocity distribution, because if you know the Newton's law of viscosity is given by tau is equals to mu curly u upon curly y. So if you want to calculate tau, that is shear stress, first of all you should know the u, that is the velocity. That's why we'll see, or we'll derive the equation for velocity here, and then we'll move on the shear stress distribution or shear stress equation. So in velocity distribution, you can say, applying the Newton's law of viscosity, which is tau is equals to mu curly u upon curly y, this particular value of tau we can try to substitute in this equation number 1 here, that is curly p upon curly x is equals to curly tau upon curly y. So let's say, substituting the value of this tau into that equation number 1, we will get this curly p upon curly x is equals to curly upon curly y mu curly u upon curly y. So the final form would be equals to mu into curly square u upon curly y square. Or in other words, making curly square u upon curly y square as the main formula will be equals to 1 upon mu curly p upon curly x. And as I just said that we have to derive the equation for the velocity here, we need to integrate with respect to y, and we have to integrate it on the both the sides. So if we take the integration with respect to y, it would be curly u upon curly y is equals to 1 upon mu into curly p upon curly x into y plus c1, because this curly p upon curly x is constant, so it will not come under integration, it will come outside the integration as a constant. So here if you see, this c1 is the constant of the integration, but we have marked as c1. This is the first integration, because we have to go for another integration to get the value of u. So integrating again, the form will be equals to u is equals to 1 upon mu curly p upon curly x y square by 2 plus c1y plus c2. Giving this equation is equation number 2. This is the form, you can say, is a general form for the velocity in this case. But here if you see, we have two constant of integration, c1 and c2, and we need to get the values of this c1 and c2 to get the final form of this equation. So this value of c1 and c2 can be obtained by using some boundary condition, and here we are going to use these boundary conditions as two different boundary conditions. The first boundary condition we'll use as at y equals to 0. That means from lower fixed plate, if you consider some distance as y, but here you consider when there is no y available, when y equals to 0, if you put that y equals to 0, your this term will become as 0, so your u will be equals to 0. And as you will take this y equals to b, the total distance between these two parallel fixed plates, so your u again would be equals to 0. So because we know very well, because if you try to put this y is equals to b here, and we have also seen in the last case that the velocity at the boundaries or the surfaces would be 0, because in this case since the both plates are not moving and they are fixed, that's why this velocity u is equals to 0 at y is equals to b distance, or for that condition. So we have these two boundary conditions, and we can substitute these two conditions one by one to get the values of c1 and c2. So let's say, substituting the first boundary condition in equation, we will going to get this c2 is equals to 0. And if you substitute the second boundary condition into that same equation, we're going to get your form of c1 is equals to minus 1 upon 2 mu curly p upon curly x into capital B. So with these two values c1 and c2, we can substitute these two values c1 and c2 here in this equation number 1 of u, equation number 2 of u, and we can derive the final form of the equation of velocity. So let's say, substituting the values of c1 and c2 here into this equation number 2, we will get the final form of u, or that is velocity u, is equals to 1 upon 2 mu into curly p upon curly x into by minus y square, giving this equation as equation number 3. So this is the equation of the velocity distribution here in this case. Now if you see this equation, your velocity u varies with the square of y, which means the velocity distribution curve for viscous flow between these parallel flat plates is a parabola, with its vertex being at the center point between the plates. That means the maximum velocity will occur at the midpoint between the plates, and we'll see first of all the distribution, how this velocity will going to distribute. So this is the diagram I have prepared for the velocity distribution. So these are the two plates which are now located at b distance apart, and they are the fixed plates, and this right sign or right arrow is indicating the direction of the flow. So this parabolic curve, or this curve, is indicating the velocity distribution. As you can see, the maximum velocity will occur exactly at the midpoint between these two parallel fixed plates, that means at distance b by 2. So that means to achieve the value for maximum velocity, as we have just discussed, the maximum velocity will occur at midpoint between the plates, and therefore we have to substitute the value of y in that equation is equals to b by 2. So if we substitute the value of y is equals to b by 2 in this equation, we'll get this u max is equals to 1 upon 2 mu into curly p upon curly x, that is in minus, into b square by 4. Right. So this is the case of u max. So in other words, we can say your u max is equals to b square upon 8 mu into minus curly p upon curly x. So this is the equation for the maximum velocity, and as we have just seen, the maximum velocity will occur exactly at the midpoint between these two parallel fixed plates. Right. Now as we have derived the form of this velocity and this velocity, that is u max, now we can go for the shear stress distribution. So first of all, let me remind you that this velocity distribution in this case is exactly same as we have seen in the case of this circular pipe. So but in that case, the maximum velocity was occurring at the center of the pipe, but here you have to mark that it will occur exactly at the midpoint between these two parallel fixed plates, right? So moving further, we'll see now shear stress distribution. So shear stress distribution, if you see, what we can do, we can again now use the law of viscosity, that is Newton's law of viscosity, and we can use that equation called tau is equals to mu into curly u upon curly y. What we can do, we can substitute the value of u, that is the velocity here in this equation, to get the final value of tau, that is shear stress. So if we do that, the tau would be equals to, after simplifying, minus curly p upon curly x into b by 2 minus y. So this is the general form of your shear stress, and this is how your shear stress will going to distribute across these two fixed parallel plates. So if you see this equation here, it clearly indicates that the shear stress distribution is linear in the case of viscous flow between these two parallel fixed plates, and that I have shown in this figure, right, by this diagram. So that means when your y equals to b by 2, that is at the midpoint between these plates, your tau would be 0, and it has maximum value at either boundary, that is at y equals to 0, or let's say when your y equals to total b. So if you substitute the value of y equals to 0 in this above equation of the tau, we'll get tau max is equals to minus curly p upon curly x into b by 2. So this is the equation for your maximum shear stress, and this is the diagram showing the shear stress distribution. So these are two parallel fixed plates, and this capital B is the distance between the two plate, and this is how your shear stress will going to distribute. So you can see it is distributing, or it is varying linearly from the midpoint towards the boundary. So tau is 0 exactly at the midpoint, and it will go on increasing as you move away from the midpoint, and it will become maximum at the boundaries of these plates, right? So this was the case for shear stress distribution. Again, you see this is the same variation or same distribution as we have seen in the case of circular pipe, right? So after getting this velocity distribution and shear stress distribution, I said that we're also going to see the ratio of maximum velocity to average velocity, right? So what we can do, as you know very well, that we have derived maximum velocity. Now before starting with this ratio, we have to derive average velocity. And as you know that average velocity can be obtained simply by having the discharge. So what we need to do, we have to consider the discharge per unit width of the plate, and that can be obtained simply by integrating a small discharge, let's say dq, assuming which is passing through a small strip of width, let's say dy. So that's why the discharge per unit width of the plate, you can write it as dq is equals to u, that is velocity, into dy, right? Because we have assumed that this small discharge dq is passing through a strip of width dy, as we have seen, or we have assumed in the last video for this viscous flow when it was passing through a circular pipe, and we have considered that the discharge was passing through a small circular concentric ring of thickness dr, right? So this is the similar way we have considered that the discharge is passing through a small through a strip of width dy, right? So we need to obtain discharge first of all to get the average velocity. So if you see here, we can substitute the value of u into this form. So the dq would be equals to 1 upon 2 mu into minus curly p upon curly x into by minus y square, that is the equation of the velocity into dy. So let's say integrating both the sides with limits from 0 to b, will get the q is equals to 1 upon 2 mu into minus curly p upon curly x, which will come outside of the integration, and after integration this term will look like as b into y square by 2 minus y cube by 3 for limit 0 and b. Now applying the limit here, your q would be equals to 1 upon 2 mu into minus curly p upon curly x into b cube by 2 minus b cube by 3. So we can take the common term in denominator here. So it would be 6. So 6 will be multiplied with the 2 outside. So final form of the q will be equals to b cube upon 12 mu into minus curly p upon curly x. This is the discharge what we have get. Now we have to obtain the average velocity. So average velocity is nothing but is discharge by area. But here if you see, here it has written as u average is equals to q by b. So the area we have to consider is, it is now nothing but it is your discharge per unit width we have considered. That's why it is q divided by b only, right? So now substituting the value of q here, the form for u average will be equals to b square upon 12 mu into minus curly p upon curly x, that is the average velocity. So hence the ratio of the maximum velocity to average velocity, if we take, it will be equals to b square upon 8 mu into minus curly p upon curly x whole divided by b square upon 12 mu into minus curly p upon curly x. So the common term will going to get cancelled. Let's cancel it. This term will going to get cancelled. This b square will cancel. This mu will get cancelled, and if you simplify this term, it would be 3 by 2. So is equals to 1.5. That means your maximum velocity is equals to 1.5 times the average velocity. So in the case of circular pipe, it was is equals to 2 times average velocity. Here it is 1.5 times, right? So this is the case for the ratio of maximum velocity to average velocity. Now moving further, now we'll see the pressure drops in terms of average velocity. So pressure drop is nothing but is your drop of pressure or the loss of head. In other words, you can say, we can write it as loss of head. So what we can do, we can use the equation we have just, or we have further, first of all we have derived, that is minus curly p upon curly x. But this is not the equation. Let me show the exact equation. So from equation number 7, so your equation number 7 is here, right? This is the equation. Yeah. So if you see here, this is your equation, this one. Your u average is equals to b square upon 12 mu into minus curly p upon curly x. And now we are interested here in this term called curly p upon curly x, which is nothing but is your drop of pressure. And as we have seen, we have to show this pressure drop in terms of average velocity. That's why we are utilizing this equation of average velocity here. So we can write this equation in terms of this pressure drop. So that's why this equation is now looking like this: minus curly p upon curly x is equals to 12 mu u average upon p square. So for pressure drop, first of all we have to consider some finite length of this plate. So considering the finite length of, let's say, capital L, so pressure drop P1 minus P2 for your length L will be equals to 12 into mu u average upon B square. So if HF, let's say, represents the loss of head or loss of pressure head, then your HF would be equals to P1 minus P2 upon gamma, and gamma is nothing but is your specific weight of the flowing fluid. So this HF would be equals to 12 into mu into U average into L upon gamma into B square, because if you substitute the value of here P1 minus P2 in this form, then this term gamma will come in denominator and L will be multiplied here in numerator. So your head loss of pressure, or the head loss of pressure head, would be equals to this form, or this equation number 10 you can see. So now this was the case for your viscous flow of fluid when it is passing through two parallel fixed plate, right? So as I've discussed in the beginning of the video, that we're going to see the example also. So here is the example data I have just mentioned, and I'll try to solve this example for you. I have solution available with me, but I'll make you understand how to use this equation and how to understand the term. So let's first of all read the data which is given to us. So we have given the oil is flowing between two parallel plates, and these plates are kept at a distance, let's say 0.08 meters. So this would be capital B, and it is with flowing with a maximum velocity of 1.6 meter per second. So maximum velocity, that means u max we have given. Now also we have given the viscosity of oil equals to 2.1 Newton second per meter square. So with this data, we have to solve four different objectives. So the four objectives are: we have to compute discharge first of all, second we have to compute shear stress tau, also we have to calculate the pressure difference between 2 points at 50 meter apart. Let's say if you consider the 2 points are now located 50 meter apart, from first point to another point, what would be the pressure difference or pressure drop. And the fourth objective we have to see for this example is velocity at 0.02 meter from the plate. So the 0.02 meter is nothing but the y distance is given to you, and that from that you have to calculate the velocity here. So let's start solving this example. So how we can do that? So in terms of solution, we can begin with the first of all discharge. So now if you know the discharge, if you want to calculate, so we know that your average velocity is discharged by area. So we want to calculate discharge here, so we have to multiply this area into average velocity. And before that, area is now maybe, let's say, available considering the unit width of this of the element here or the plate. So the u average is not available. So first of all we have to calculate, or we have to compute the average velocity. So the, let's say, your average velocity as u average is nothing but equals to, if you know, it would be equals to 2 by 3 into u max. And why 2 by 3? Because we have seen in that ratio of maximum velocity to average velocity, as your u max is nothing but is your 3 by 2 of u average, right? So that's why this u average would be equals to 2 by 3 into u max. So now we have given this u max. So u max we have given as 1.6. So if you calculate this, you will get your answer of u average here is equals to 1.11 meter per second, right? So this is the value of average velocity. Now the first objective will try to solve. The objective number 1 we have to find out is nothing but is your discharge, right? And discharge we have to calculate, but mind well, this is the discharge per unit width of the plate, and unit width, that means it's your 1. So nothing but we have to do this way. Your average velocity, your average velocity should be multiplied by with the distance between two fixed plates. So the average velocity we have just calculated is your 1.11, and your distance between two parallel plates has given as 0.08. So if you calculate this, your answer would be equal to 0.088, and that unit will be meter cube per second. But mind well, it is your per meter, because we have calculated discharge per unit width, so it would be equals to per meter. So this is the first objective we have just solved. This your discharge, right? Now moving further, the second objective, right? The second objective we have to calculate here is nothing but the pressure difference, no sorry, the shear stress at the plates, right? Yeah, we have to calculate the shear stress at the plates. So the shear stress, if you remember the form, or we have seen, the shear stress is nothing but tau is given by minus curly p upon curly x into b by 2. This was the equation we have to see. But here, if you see this equation, we have b available with us in data, but we do not have this minus curly p upon curly x. So anyhow, we have to calculate this term called minus curly p upon curly x. So the equation of average velocity we can use here. So equation of average velocity was p square upon 12 mu into minus curly p upon curly x. So if you see this equation now, we have just calculated average velocity here in the first step or in the beginning. B is available with us, mu, that is the viscosity of oil, is also given to us, and this remaining term is minus curly p into curly x that we want to calculate to get our shear stress value. So what we can do, we can make this minus curly p upon curly x as a main in formula. So the term would be equals to, what you can say, it would be u average 1.11 into 12 into mu was 2.1 and divided by your b square, that is your 0.08 square, and if you calculate this, your final answer for this term minus curly p upon curly x will be equals to 4370.6, and the unit for this would be equals to Newton per meter square, which is nothing but per meter. And this is the pressure intensity, in other words you can say. That's why the unit is per area, per meter square, right? So now this term we can try to substitute in the equation of the shear stress. So you can say hence the shear stress tau would be equals to, tau is equals to, let me write that equation again, minus curly p upon curly x into p by 2. So substitute the value of that minus curly p upon curly x, 4370.6 into the value for b is 0.08 divided by 2, and if you get the answer for this, your final tau would be equals to 174.82, and the unit here would be Newton per meter square. So this is the value of tau. We have calculated this was our second objective, right? So let's move further. Our third objective, and the third objective was to find out the pressure difference, right? The pressure difference between 2 points at 2 points 50 meter apart, right? So for this we have to calculate the pressure difference. So we have seen that pressure drop in terms of average velocity. The equation was P1 minus P2 is equals to 12 into mu into u average into capital L whole divided by p square, right? This was the equation. So we have all terms available here with us, so we can simply calculate by putting the all respective values. So let's try to substitute the values here. So it would be 12, mu is 2.1 into u average is your 1.11 into L we have to take as 50 because we are calculating this pressure difference between 2 points which are now placed apart at 50 meter distance. So add will be 0.50 and divided by b square, that is 0.08 square, right? So calculate this thing and you will get your final answer of P1 minus P2 is equals to 218,531.2 Newton per meter square. And this is the very big term, so we can further reduce this term. P1 minus P2 is equals to 218.531 kilo Newton per meter square. So this was our third objective, and the last one we have to calculate objective number 4 for this example is nothing but the velocity. The velocity at distance we have given as 0.02 meter from the plate, right? So this is nothing but, as I have just mentioned, that this is the y distance we have given to us. So simply we have to use the equation for the velocity. So the equation for the velocity of u is equals to 1 upon 2 mu into minus curly p upon curly x into py minus y square. So if you see here, we have mu, we have minus curly p upon curly x, we have also given b, and we have this y available. So we can simply put the values and we can get the answer. So let's say substituting all respective value, 1 upon 2 into mu is 2.1 into this distance, let's say 4370.6, yeah, this was the value, into your by. So b is your, you can say 0.08 into y is your 0.02 minus y square, that is 0.02 square bracket close. So the values we have substituted in this equation and we can calculate this term, and after calculating, your value of u will come as 1.24 meter per second, right? So we have calculated this example, and as you can see, we have solved all these 4 of objectives: the velocity at 0.02 meter of the plate, the pressure difference between 2 points which are placed 50 meter apart, P1 minus P2, we have calculated the shear stress tau, and also we have calculated the discharge this per meter, right? So this was the simple example I have just taken here in this video for your understanding, so that you can know how to use those equations for solving different form of examples, right? So this is it for this video. I hope you now have proper idea about this case of flow of viscous fluid through 2 parallel fixed plates, and also I hope that I made yours a bit doubt clear, right? So thanks for watching. See you next time.